Good evening, everyone, and my name is Sarath Kumar. This is a talk and series of talks on Rust. So this is a Friday talk, and today I'm going to present you one of the security vulnerability, how it occurs in different languages like C, C++, and how we are able to avoid that in Rust. And I'm going to give some of the examples of buffer overflow attacks happened in past and which were created some financial issues, such sort of financial time and value issues in a company for a company. So for a project or for a company or for people, which is created like a lot of issues, which is a buffer overflow issue. So I'm going to go through the introduction and what is buffer overflow in C and C++, how it's going to occur. I will show in simple demo how it is going to occur there, and also how it can be a security vulnerability. Going to explain that it can be a security vulnerability, and then the same vulnerability can be avoided by adopting Rust language. So that thing I will show you, and both this can avoided at compile time and also at runtime. We can avoid this vulnerability. Okay. So then finally we'll see like some of the examples of this vulnerability which is occurred in real time. So let's start with the what is buffer overflow. Basically, I'm trying to show that in a C programming language. So let's see that. Okay. And this is a typical C programming language where I'm trying to create a buffer overflow in this example. So let's see how it's going to like see. For example, I'm going to explain this code like there we are taking a command line argument, which is a string we'll take as a command line argument, and that string we are passing as a argument to this copy function. And in this copy function, there is a buffer of 100 bytes, as you see. And whatever the string we passed as a command line argument, that thing we are trying to copy into this buffer, which is of 100 bytes. So first we'll see like we'll pass like 100 bytes and we'll pass more bytes, and we'll see like what is the issue we're facing. And also we can see that we are trying to print actually it will this buffer can store only 100, but we can store more than 100 bytes easily without any issue, and we can access them, which can cause a issue, which is the cause of the vulnerability. So let's see mm, how it's happening. So I'm using GCC now here. GCC example C -o, and then I'm going to give test as this. So now I have a test function, sorry, test executable file. So I'm going to give 1, 2, 3, 4, 5, 7, 8, 9, 10. Okay. So that we'll have a proper count. Now it is 50, so I'm going to copy this. Copy, paste. Now it's 100 bytes data I'm trying to pass here. Let's see what is going to happen here. So it's done, successfully executed, and character in buffer. There is no character, but still we are able to access the memory which we not assigned or not allocated, but still we are able to access that memory. So now what we'll do, I will try to increase the memory size, like whatever the buffer, this is 100 bytes, so the buffer is able to copy properly and it's done. Like there is no issue we faced, and then no need to worry about in such cases. If suppose if you increase the size, like if you increase the size of the buffer now, so now it is 150 bytes. So now what we'll see, stack smash detected, and also we are seeing that we are able to access which we not allocated that memory also we are able to access. So what is happening here is, so that thing if we go try to understand that, so here is a stack. So the array whatever is defined here in this, we defined in this, will be stored in this stack. So after in this stack, 100 bytes will be stored, and also the return address of this, like the function return address will be somewhere below the stack. Like once the stack is filled, somewhere there will be return address. So the return address is overwritten by this, return address will be somewhere in the stacks frame. So after 100 bytes there will be return address of the uh, function, whatever the function here, copy function, there will be return address to the main function. So that return address is overwritten by this extra bytes we are providing. So that will cause, so like suppose there is a valid address of suppose this main where to return of this printf copy or printf or this copy functions return address. So that is overwritten by this a. So a means 616161, so which is like 616161 hexa address, which is not a valid address, and the code is trying to execute that address, means from that address it's trying to execute the instruction, but there is no, that is not the valid address to execute. So that's why it's giving stack smash detected or memory, like invalid memory. So we're getting, if suppose the same thing in case of instead of passing this yes, if you are able to pass proper functions address in that return address, if you are able to place a proper functions address into that memory, then the, and if the function has a proper permissions, like um, pseudo permissions or the administrator permissions to that function, then that function can do whatever, or it will give entire control of the system. Whatever the system running this application can give the complete control to the program, or the attacker, complete control can be given to the attacker. So this can be a big problem if suppose this is in a real time application. It can create lot of value and financial issues to the company once it's happened, and also resource issue it can create, and it can be create disasters if there is, it is in a like automobile or in a car software. If the same issue is found, then it can be a disastrous if someone gets a hack of that issue. So as you see in that, this is the how it's happening. So um, so the attack, I'm trying to simulate that, but it takes time. So let's, the attack I will do in the next video. But for now, we'll try to see how Rust can avoid this same issue. How Rust can avoid that, so that using Rust you can avoid that vulnerability. So let's see that how it's happening. So I have created a Rust program, similar program, where you'll have same code like this. So let's see. I have a Rust code here, which is similar. So here you can see. Here also I'm trying to create pass a string here, and the array size is this much. And here I'm trying to do deny. Okay. So now this is a code and where we created array and we are entering a string here and reading that line from the input and we're storing that input and trimming into bytes. Remove all white spaces we are trying to remove, and that input we are trying to split into bytes, and then we are trying to add. Okay, 1 second. So this code we'll add here. Control X. So so here I'm trying to add extra byte here as we did in the C language, like C program. Like here we are adding extra. We're trying to access the extra byte, or here we are trying to put data into extra byte. Similarly here what we are doing is we're trying to put data into the extra byte. So like when we're doing that, so how there are two in this. The Rust compiler can do that control of that error at compile time and also at runtime. We can do that control. So let's see like how it's happening. So now I'm trying to see the so that in compile time. So I put a denial like unconditional panic. Uh, it will not do unconditional panic. So to avoid that, we are so we'll not put this one. So we'll put this, and so that we'll run this example. We'll see like what is happening here. So as a typical C programmer, we should have feel that it will show a error. It will not show a error. But here what we'll do, we'll see. Cargo build. Build is like we are just compiling. So so here showing index out of bound is a length 10 byte, but the index is 11. But if the same code is in C language, then it will allow simply it will allow it, and it's saying that we can put this line so that it can do the compilation like denial. It's doing this is enabled, so that's why it's not compiling. So uh, so what we'll do is we'll enable the panic here so that at runtime it will panic. So at compile time it will deny the at compile time we're allowing this panic so that the panic is enabled. So at runtime it will generate it. So at compile time we're avoiding the error check. So we're telling the compiler to check the error at runtime. So now here if you run, if you again build that same thing, so you can see that clearly. If clear this, now if we build again, clearly you see the same code. I have not changed, but we said allow unconditional panic. So we are saying that compile time don't panic and run. So the code is compiled now. So now try to run that code. So if you run this code, what is happening we'll see. If you enter some a, I'm trying to increase sorry, more than 10 bytes. So this is 4 4 uh, 10. So one more 11 bytes I'm trying to put, whereas I have given only 10 bytes. So we'll see. At runtime it is panicked now. So whatever the issue is seen in C program, that is not allowing in Rust at compile time and also at runtime. Both times we are getting a panic when you're trying to access memory out of the bound. Like if you're trying to access memory of the array out of the bound, like if you're going like we are allocated 10, you're trying to access 11th byte, then it is throwing error at compile time and also at runtime. So this error will not be repeated, so that the security vulnerability what we are looking now, the buffer overflow issue will not come into picture, which can be a great thing for an security perspective or for an hacker's point of view. It cannot allow that such sort of issues. And also there is, it will avoid the programmers burden, like no need to think that the programmer whether he is creating a issue or not. So the compiler itself will take care, whereas in C++ the programmer has to take care, and where it is going wrong, all these things the programmer can miss sometimes, but the compiler will not miss. It will give the 100% guarantee of memory related stuff, like memory related issues will not be there. If once it's compiled, that means it's 100% guarantee that there is no memory issues like this. So that is very important because you can see that how the memory related stuff had happened, like the buffer overflow attacks happened in the cyber security attacks. Like there is Mori's bomb in 1988, which is a memory buffer overflow attack, and 2001 there is a attack, 2003 there is a attack, and you can see list in every now or then there is a attack. Even recently 2018 there is a attack, and also there is a um, log4j log4j attack, which is also a buffer overflow attack. These are the attacks which will created a lot of issues for the company as a value and all this stuff. As you see that crucial for software developers has to check this vulnerability when they are writing the code. So but it is most of the time it is very difficult for a programmer to check all these things. So whereas the compiler can give them, means software can give a 100% guarantee, which is implemented in Rust programming language compiler. So and if you Rust, how it is giving this guarantee is because the Rust on the other hand is designed to prevent buffer overflow problems through a combination of ownership and borrowing and safety checks at compile time and also at runtime. In general, it is not only at compile time and also at runtime the Rust is giving uh, safety. Not only at compile time and also at runtime, the Rust is giving safety. So please, like, sorry. So that's why we have to carefully choose the uh, Rust language, which is very important for our use to avoid such a memory-related bugs and security vulnerabilities. Rust can be useful. And thank you for your time.